In the second video, I'm just going to finish this problem with the bacteria growth, and then I'm going to move on and do another similar problem that involves Newton's law of cooling. It's got a similar concept to it. So we had just gotten right here an equation for the bacteria that's dependent upon time, and we did it. I'm trying to get rid of that blue line there. Let's see if it'll go. Oh, it's not going. Anyway, I do want to stress that you don't really have to memorize this right here. Let's suppose that you had forgotten, and I'm going to go over here and kind of, again, do the derivation of this particular solution. So we have our initial model that said that the rate of change in the bacteria over time was directly proportional to the amount of bacteria present. And let's suppose that I forgot that I could just write this model. Well, how would it fall out naturally? So I'm going to do a derivation of it just so you can kind of understand the importance of not having to memorize, have something to fall back on. If you forget the formula that your dy dt is proportional to y, and if you forget that that means that y is equal to the amount you start with, e to the kt. But if you forget that, well, here's how it would fall out naturally, even if you forgot. You already know how to separate variables. So I'd say 1 over b db is equal to k dt. We know we need to integrate, right? And we know that the integral of 1 over b is the natural log of technically absolute value of b. And we know that the integral of a constant is the constant times t. And then we have that arbitrary constant that hangs around. And then we know that to undo our natural log function, we would do e to that power, and we do e to this power. And it just falls out naturally. I end up getting here b is equal to, and again, we split this up into 2, and we've got an e to the c, which is just some other constant, e to the kt. Now, they told me that initially, which means at time 0, there's 5 million bacteria present. So when I put in a 0 for time and a 5 for the bacteria count, I get 5 million is equal to some constant times e to the 0. Well, that's just 1. So I get that my constant right here is really 5. Well, that was the amount of bacteria present at time 0. So it falls out really naturally, even if you forget the pattern. So let's go down and answer these last questions. It says, what will the bacteria population be one full day? Well, what this does, the solving of this differential equation, is it allows me again to predict the future with this. I've got my model that says that my bacteria count is equal to the amount I started with, e to the k, which we found by 1 times time. Well, I'm doing this for a full day, and my time is in hours, so I put in a 24. And if I go to my calculator, it's going to give me a bacteria count of about 73.789, and this is in millions. Okay? So over here, part B, I want to know, well, how long will it take for the bacteria count to be up to 1 billion? Well, remember, this problem we're doing, this is all in millions. We had 5 million, 7 million. Right here is about 74 million. So when I'm working with 1 billion, I have to express that in terms of millions. So here's my model that I've got. Okay, oops, sorry, that's a T. And I want to know how long it'll take, so I'm going to be in search of the time that it takes for the population of the bacteria to reach 1 billion. Well, 1 billion is 1,000 million. So I'd have 1,000 million, or 1 billion, is equal to 5 million e to the 0.112 times time. Again, this is one we're going to be solving for time, which is up in the exponent, so you should kind of predict what's going to happen. But I will do 1,000 divided by 5, which is 200. That's got to equal e to the 0.112 t. Now, in order for me to get up into that exponent, I take the natural log of both sides. So I've got natural log of 200 is going to be equal to the natural log of e to the 0.112 t. And we know that our properties, this comes out front, ln e is just 1. So I end up with the natural log of 200 is equal to 112 thousandths times t. And when I do my calculator division on that, I'm going to get, it's about 47.24 hours, I believe, if you go do that on your calculator. All right, so that's what we're doing with exponential growth. It all boils down to basically one general fact. And that, again, I'm going to repeat it one last time, is that when you have a quantity whose rate of change over time is directly proportional to the amount of the quantity present at that time, we can get a formula that'll allow us to predict how much is there going to be in the future. Well, it always turns out that it's the amount you started with times e to the kt. And again, this is usually represented as, it'll say initially, or at time 0 there was x amount present, y at 0. So we're going to move on to another interesting problem that's similar, not exactly the same, but we're going to apply what's called Newton's law of cooling. What Newton's law of cooling says is that the rate of change of the temperature, and I'm going to change this to capital T, I like that better than using a Y. So the rate of change of the temperature of an object, well, let's write what that means. The rate of change is the derivative, and this is its temperature changing over time. So the rate of change of the temperature of an object, again, is directly proportional, which is a k, some constant multiple, and this is of the difference between the temperature of the object. It doesn't say it's directly proportional to the temperature, it says to the difference, I'm going to be subtracting, of the object and the temperature of the surrounding medium, which we're going to call M. I kind of want to explain what that means. What that kind of means is that if you were to take, say, a hot probe and stick it into a bucket of ice water, the surrounding medium would be the ice water. In a case where you take something out of the oven and you just let it sit on the counter, if the temperature of the room is 72 degrees, we'd call that the temperature of the medium. So it's the temperature of the surrounding atmosphere, whether that be air or water is generally the case. So what I've got going here is I've got probably a room set to 75 degrees. That would be called the surrounding medium. A pizza is taken out of the oven at a temperature of 350 degrees. That means at time 0, the temperature is 350 degrees, and at that time it starts to cool. So 5 minutes later, the temperature is 112. I want you to realize that when they're giving you these 2 points right here, this is going to be helpful, and this. We're going to use both, and I want you to see how we use both of them in this process. I have to find an equation that models the temperature of the pizza at time t. So really what I want to do is, again, solve this to give me an equation for t. Well, it's the same process we've been doing. It first requires a separation of variables. So what I'm going to do initially here is rewrite it and replace the one thing I do know, and that is that the surrounding medium was 75 degrees. So now as I go separate my variables, I've got 1 over t minus 75 dt is equal to k, change in time. All right, so that's my first thing, is to separate those variables. I want to move my screen up a little bit here, get some more workspace. All right, and then we've been doing this for so long, you guys know. We're going to integrate next. So again, the integration of 1 over t minus 75 is just ln, absolute value of t minus 75, technically then times the derivative of that, but that is simply 1, so I'm fine right there. And that's plus some constant, and again it's going to equal kt plus, and we'll put all our constant over here on the right-hand side. Now, because the room is 75 degrees, we can safely assume that this is never going to go below that. I mean, it can't go below the temperature of the room. So we're very safe to just drop those absolute value bars, just as we kind of have been with most of the word problems. All right, there we go. But that's an explanation why in this case you can drop them. All right, so next thing, in order for me to get in here at this t, I'm going to have to do my e to the ln t minus 75 is equal to e. Again, this process is so rhythmic, you're probably almost sick of it, but it is kind of important. It allows us to get us a very good equation that, again, allows us to predict what's going to happen in the future or predict the amount of a quantity at a different time. So what I end up with on this one is, again, the e and the natural log basically are inverse functions. So I've got t minus 75 is equal to e to the kt times e to the c, which as usual, we're going to make that our own big C. So I've got the temperature minus 75 is going to be equal to a constant times e to the kt. So this is where I'm sitting at right now. What I'd like to do now is, I could add the 75 to both sides, or really what I'm going to go do now is use the fact that I know that at 0, the pizza was 350 degrees. So again, when I go, I'm going to go get that constant right now, this one out front, because when I put 0 in for time, I end up with e to the 0, which is just 1 over here. So really what I end up getting is that my 350 degrees minus 75 is going to be equal to c times 1. So what that allows me to do is get my constant out there, which is going to be 275. All right, so now I'm ready for a rewrite. I'm going to go back up here and we're going to rewrite that. I've got t minus 75 is equal to 275 e to the kt. Well, I'm going to move that 75 over here. I could have done it before also. Doesn't really matter. It's a piece. So here's my equation as it stands. Well, now the only thing that's unknown here, and I should be using a baby t for time just so you don't get confused. The only thing that's unknown right here is this constant k that was, our direct proportion constant. Well, they gave me another piece of information that I'm going to use to find that, the second piece. And you generally do always use your initial point first to find the constant out front, and then we're going to be using our second point that we know that after 5 minutes it had cooled to 112 degrees. And we're going to use that to help us find the k. So I know it's 112 degrees, and that's at time 5, so I'll put a 5 in there for t, plus 75. I'll subtract the 75 and I get 37 is 275, and you can see where this is going. And again, solving for that exponent, it's got a rhythm to it, so I will be dividing. And I will natural log both sides. All right, 37 is equal to the natural log. We'll basically undo that. The exponent comes out front. We've done that a couple times. So really what I need to do on my calculator to figure out that k is the natural log of 37 over 275 divided by 5 is going to be equal to k. And I haven't done that yet on my calculator, so I'm going to have you can just do that on your own. And you're going to get that k. Usually we round it to 3 decimal points. And so for us to complete our answer, we are being able to predict the temperature at any time in that cooling process, which would go from 350 degrees down to the room's temperature, which is 75 degrees. So at any time, I can say at 275, again, we're going to have a limit as t approaches infinity. We call this a limiting amount, but as t approaches infinity, we're going to end up having a limit of 75 degrees. Kind of makes sense. So where am I here? I've got 275 e to the k, which I need you guys to go wrap that up. I don't know what that is, so I'm going to just leave a space there. I don't have my calculator out with me right now. T plus 75. So that's how we use Newton's law of cooling. Now you might say, who cares about a pizza? And honestly, not me. But you're going to have a problem on your packet where you can use this to actually, for a little bit more forensics method in trying to find time of death. And so what's going to happen in that one, and I'll talk till I run out of time, but there's one in your notes that I labeled dead bodies where a body's been found in a hotel room, and they tell you what the thermostat was set to or what the temperature of the room was at the time they found the body. So you can assume that we would call that the temperature of the medium, or the M in the problem would be the room temp when they find the body. You're going to use that, and you're going to use this Newton's law of cooling to predict the time of death. And I'm going to give you a little hint on that. One thing that you're going to do is you're going to go get your equation right here using a similar process to what I just did up here. But then you're going to actually be predicting the time of death. Well, you got to kind of realize that a body's temperature at the time of death, unless the person has a fever or something, is about 98.6 degrees. So you're going to set that equal to your equation, which is going to have a little e to the something t in it, whatever your k is. And you're going to be solving that for time. And when you do that, so when you get your solution up here, going through this whole process, you're going to take it one step farther and say, okay, I want to know when that person was murdered. Well, how do I know that? Well, I set the body temperature equal to 98.6 degrees, and I solve for t. So you are to do the 1, 3, 5, 7 in dead bodies in your packet. Have a great day, guys.